More conservation of energy, G. So here's another lovely example. A slingshot is a good example of the law of conservation of energy. A slingshot is pulled with an average force of 70 newtons for a distance of 90 centimeters. How much potential energy is stored in the slingshot? First of all, potential energy here, are we doing work against gravity? No, so don't write this down. Would I go potential energy is mgh? I mean, you might, isn't that the height? Look at the picture. Is that a height? Is that a height? No, it's not vertical. We're not doing work against gravity. So how much potential energy was stored? How could I figure that out? Another way to think about energy is the ability to do what? Work. Okay. Work is force times distance. So the potential energy is the work, it's force times distance. It's going to be 70 times, nice try, Mr. Dewick, not 90, 0.9. And I think if you do that on your calculator, you should get 63 joules, I hope. If there is a 35-gram mass in the pouch, how fast will it leave the slingshot? Ooh. What's this question asking me to find? How? Kessler thought for a while, and then his eyes lit up. Conservation of energy? What did I find in part A? Darn right, conservation of energy. Yeah, I think so. So I think our argument here is going to be kinetic initial. Don't write this down. Don't write this down. I could go with that. And if you did, I'm fine. But I think here, if we wanted to get there a little shorter, what's the energy transformation that's going on? All of the potential is turning into what? If you wanted to, you could just say, write this down, that equals that. Potential initial equals kinetic final. What's the potential initial? 63. That equals a half mv final squared. This is the same math that you were doing in the lab to figure out your launch speed and your impact speed. You knew how much potential energy there was. You knew the mass of the object. How would I get the v by itself? Times by 2, divide by m square root, or Owen, divide by 0.5 and m square root. V is going to be 2 times not 0.63, Mr. Dewick, times 63, divided by, oh, nice try, Mr. Dewick, 35 grams. How many kilograms? 0.035. This might work out evenly. 60? Does that seem about right? Half a football field, and it's like, I've seen slingshots. They go pretty fast, but not so fast that I can't see the rock move. I like this question. I like this. And here's what drives me crazy, okay? This is where I know people haven't understood the material they're trying to memorize. They see part A, and they go like this. And then they panic because I didn't give them mass. Oh, but they're clever. They read part B and they say, oh, he did give us the mass, as though somehow I give you something that you needed later on instead of when you need. I've never done that to you, and I never will. I've never said, oh, you need something from part E to solve part A. I don't work that way, but okay. So kids go 0.035 times 9.8 times 0.9, because, oh, that must be a height because it's meters. Are you doing any work against gravity? No, to me, this is like a panicked, not really understanding what's going on here. And then they use that to find KE. Please don't. So probably in your future, either a bow and arrow question or a slingshot question or something along those lines will show up in your future. Because those are nice applications. Example 2. Tarzan runs at 82 kilograms, weighs 82 kilograms and can run at 8 meters per second. He runs along the ground and grabs a vine swinging into the air. Liz, what's this wanting me to find? Height. Let's dolp. So here's Tarzan. Running along. And here's the ground. And let's say here's the vine. So he's going to grab the vine. Let's make the vine a little lower. He'll grab it like waist height. Okay? And he's going to swing into the air. And it wants us to find that. Liz, any suggestions on what approach I might use for this? Can you generalize more? It may be included in the title of the lesson. How would I know to use the law of conservation of energy? Is there a change in height when he grabs the vine? Will there be a change in speed when he grabs the vine? Is there a yucky, curvy path? Bingo. Okay? So I'm going to start out with KE initial plus PE initial equals KE final plus PE final. Are any of these 0? Well, there's a bit of a tricky issue here because the ground is here, not... Wait. Can't we put the ground wherever we want? Alicia's nodding. Alicia, let's add a little dotted line right here. Let's put the ground there. Let's do ourselves a favor. So, Liz, what's Tarzan's initial potential energy if we're talking gravitational? Yeah, PEI is not a real province. Is anything else 0? Yeah, I think if we're talking maximum height, you got to imagine now, I think slowing down, briefly come to a. So we're going to have this. A half mv initial squared equals mgh final. Oh! Liz, what else do you notice? What does that mean? Well, Liz, it means that not only will Tarzan swing to this height, but Tantor the elephant, if he was running along at 8 meters per second, assuming the vine didn't snap, he would swing to the same height as Tarzan. Kind of cool. What are we trying to find? Get the h by itself. So I'm going to write it like this. H final equals VI squared over 2G. Or Owen could write it as 0.5 VI squared over G. Liz, what happened to the 1/2? It's still there. I just didn't write the 1 because timesing by 1 doesn't make a difference. Okay. What do we get? You'll get 3.27? Slap shots are really, really good examples of energy transformations. And I have a video, but we'll show it at the end of the lesson because it's a long one, but it's really interesting as well. Let's keep going. Ooh, more roller coasters. The roller coaster below has a mass of 255 kilograms. If the coaster just barely makes it over the first hill at A, how fast will it be going at B? In other words, assume VI is 0. So, any suggestions on how I might want to solve this? Why? How do you know? Is there a change in height? Is there a change in speed? And especially, is there a yucky, curvy path? We want a scalar, not a vector approach. We want something that doesn't require me to know every one of those angle thetas and solve. So let's use the law of conservation of energy, G. All right, folks. Are any of these zeros? Yep. Which one? You have to say initial or final. I got 2 KE. We'll do that when we analyze roller coasters. If we do manage to get to our Playland physics field trip, coming over the first hill, you're usually going pretty slowly. Although you can calculate that speed if you really, really want to be nitpicky. It's not that hard because you're not accelerating. It's D equals VT, V equals D over T. But often we'll just say, let's assume we started pretty close to it rest. Anything else, Zero? Are you saying that this is the same physics as the rope swing? Almost. In the rope swing, we turned kinetic into potential. Here, we're turning potential into kinetic, but it's a similar transformation of energy. So we're going to end up with cool. Zena, have you been on a roller coaster before? Before you got on the roller coaster, did they make you stand on a scale? Why not? All right. They want us to find V. V final is going to be the square root of 2 GH. 2 times 9.8 times 18. Again, if your calculator doesn't extend the square root bar, you'll have to put it in brackets or square root and then equal sign, or multiply it and then square root enter button. You get 18.8? Is that right? And then because I'm a coaster nerd, I always go times by 3.6. How many kilometers per hour is it? Meh. This is an okay coaster. This is not one I'm lining up for 2 hours to go on. This would be my, it's only a 10-minute lineup. I'll go on that one, fine. Suppose the roller coaster had an initial speed of 22. Now how fast will it be going if we ignore friction? Okay. It's going to be a real similar setup. But this time, I think, Spencer, you'll agree only PE final is 0 because it's telling me clearly that there's an initial kinetic energy. Hopefully this will be a bit of a better coaster now. I'm going to get a half m v initial squared plus m g h initial equals a half m v final squared. Deegan, have you been on a roller coaster before? Before you got on the roller coaster, did they make you step on a scale? Can an empty coaster car make it through the track the same way as a full coaster car? Why? And then, what am I trying to get by itself? I could, if I was Owen, divide by 0.5 square root. I have a little clever trick that I do. I clear fractions. I actually go times by 2, times by 2, times by 2, because those halves all cancel, and I end up with this. Vi squared plus 2ghi equals Vf squared. And I kind of always smile at that one because it's a bit of an error check. I showed you this is actually Vf squared equals Vi squared plus 2ad in disguise. So it's also kind of a, hey, I know I probably set this one up right. Square root. Going to be the square root of 22 squared plus 2 times 9.8 times 18. 22 squared plus 2 times 9.8 times 18 square root answer button. Oh, that's a better coaster. 28.9. Multiply that by 3.6. How fast are we going? How fast? Okay, that'll stand in line for. C. Suppose the roller coaster in part B is only traveling at 25 meters per second at the bottom. How much energy was lost to heat? What does this want me to find? So I'm going to modify my conservation of energy equation. It's going to be KE initial plus PE initial equals KE final plus PE final plus heat. I can still say potential energy final is 0. Spencer, what am I trying to find? How would I get the heat by itself? This is the weird equation where people sometimes divide. I don't know why, but yeah. So it's going to be heat is equal to initial plus initial minus KE final. What we're really saying is, here's all the energy. You lost some to kinetic, but not all of it. The rest of it must have gone into heat. We're going to get heat equals a half mv initial squared plus mg h initial minus a half mv final squared. Ooh. Annika, do the m's cancel this time? Why not? Isn't there an m in everything? What isn't there an m in? And so have I lied to you a little bit? What I said to you is, as long as we grease the track down so that we lose very little energy to friction, then the masses are negligible. They don't quite cancel out in real life, but close enough that an empty car and a full car will make it through just fine. By the way, because they don't cancel out on really good coasters, like really intense ones, they do actually have to include a couple of spots along the track where they break you, where they slow you down. So if you've done, for example, California Screaming, there are a couple of spots there where they suddenly slow you down because the masses technically don't cancel. And in particular in California Screaming, they've got a pretty intense loop. You have to hit that speed within a fairly narrow margin. Okay. Heat is going to be 0.5. What was M? 255. And was VI 22 plus 255 times 9.8 times 18 minus 0.5 times 255 times 25 squared. Logan, what'd you get? 27004. Anybody else? Yeah, so 27,000, I guess, if we go to 3 sig figs. Joules of energy. Mr. Dewick? Yeah? That's wasted energy. Is there any way we could use that? It'd be kind of neat if we could. That's what regenerative braking systems on electric cars do. Rather than bleeding the energy off as heat, we bleed the energy, the kinetic energy off as electrical energy, and we use it to recharge your batteries. Still not perfect, not 100% efficient, but that's why as soon as Priuses came around, every taxi cab driver, or most of them, switched to a Prius, to a hybrid, because every time they're hitting the brakes, they're recharging their batteries. So they get very, very good. Priuses get better gas mileage in the city than they do on the highway, where most cars get much better. Internal combustion engine cars get better mileage on the highway, terrible mileage in the city. Hybrids, it's the opposite. Example 4, a cart and rider start from rest. I would underline the phrase from rest on a 20-meter high ramp. At the bottom, the car is traveling at 15 meters per second. How much energy is lost to heat? Okay. Is there a change in height? Is there a change in speed? Okay. Is there a yucky, curvy path? Is this question talking about heat? That's also a job for conservation of energy, G. Okay. So if the question is mentioning heat, probably you want to handle that with this. Mr. Dewick, do I need to write out the terms that I know are 0? No, if you were clever enough to say, oh, they said from rest, so KE initial is 0. Oh, and I'm ending up on the ground, so PE final is 0. If on your first line, Rachel, you just wrote all of the potential energy initially is going to turn into kinetic energy and heat, I'm fine with that. How would I get the heat by itself, Shay? Wouldn't I divide? No. So you're telling me heat is going to be the initial potential minus the kinetic final. You're telling me heat is going to be mgh initial minus a half mv final squared. Oh, I like this question. I like this question. I like this question. In particular, I like part B, which we haven't got to yet. Do the m's cancel, Shay? Okay. It's going to be 75 times 9.8 times 20 minus 0.5 times 75 times 15. Squared? Oh, squared. Thank you. Wow. Dewick. 75 times 9.8 times 20 minus 0.5 times 75 times 15 squared. Do you get 62.5? I'll write it to 3 sig figs, but I'll store this on my calculator, just in case. Alicia, what's B want me to find? So don't write this down. Alicia, my first thought would be, well, friction is mu times the normal force. Did they give us, don't write that down, did they give us a coefficient of friction, a mu, in the question anywhere? Whew. The normal force would be mg perpendicular. Did they give me angle theta? Now, I mean, I could use trig to figure out angle theta. It would be shift sine. I could find it, but I still don't have a mu. I don't think I'm going to do that. What did we, so then my mind would say, well, maybe I can use something from part A. What did we find in part A? What's another way to think about the energy lost due to heat? The work done by what? work done by friction. I can say the work done by friction is the force of friction times distance. But instead of the work done by friction, I'm going to think heat. That's the 62 point, whatever goes there. Alicia, get the friction force by itself. How will I move the D over? Yep. So yet another way to find friction, we've got several, but another way to find the force of friction is going to be, I'll even write heat divided by the distance that the heat is exerting its heat for. So it's going to be 62.5 divided, which distance? There's no horizontal distance in this whole question. That's a bad guess. In the same direction as the force, because that was the condition for work. For work and distance, the distance had to be in the same direction as the force for force times distance. So going to be divided by 60. 60. Why did I write 20? I thought 60. The average force of friction is 104 newtons. Okay. Rube Goldberg machines are great examples of energy transformations. So Rube Goldberg, I think I mentioned this to you a few days ago, was a cartoonist, I think for the Saturday Evening Post, and he loved drawing very elaborate chain reaction contraptions to do very, very simple tasks. And so, for example, we might have, I don't know, looking for a few here. Let's go Physics 11, Mr. Dewick. So put your pencils down, look up. Oh, wrong one. Too much stuff on my website. What do I call this one? The blue marble. So, I mean, that was just to get it in the cup. That wasn't much of an actual useful task. It's a little nicer if you can actually do a fairly useful task. This is a really neat one. So the gas is evaporating, condensing on the sponge, and making the sponge, as it condenses, just heavy enough to tilt it up. So there was your simple task. Just realized I forgot to have my headphones plugged in. Sorry about that. You're getting lousy sound. Another great example of the law of conservation of energy, is a bouncing ball. So if we take a basketball, at the top of the bounce, what type of energy does the ball have? When the ball hits the ground, what type of energy does it have? Now, I've noticed that if I just let a ball bounce, it loses height on each bounce. Does that violate the law of conservation of energy? Why? Sorry?
It goes to sound and heat.
No, we lose energy to sound and heat. Far more heat than you realize, actually. Oh yeah, basketball players all know when the basketballs are stored in the trunk overnight, which happens, or they left it in the car overnight. In the morning in the gym, you pound the balls against the floor, and you get the gas inside the balls to slowly heat up, and that's enough so that they'll bounce properly again. Right? Is it possible for a ball to bounce higher than it was originally dropped?
Not unless you change the functions of the ball. Throw it.
Unless I cheat. So do you understand why I said the answer to D is no unless I cheat? Okay, unless we're clever. A golfer wants to hit their drives further by increasing the kinetic energy of the golf club when it strikes the ball. Which would have a bigger effect on the energy transferred to the ball by the driver? Doubling the mass of the club head or doubling the speed of the swing? Why doubling the speed? Okay. Since kinetic energy equals a half mv squared, Logan, you're right. That right there, if I can double the speed, how much more energy will I have? What's 2 squared? 4 times the energy. In theory, 4 times the distance. Air resistance, but in theory, 4 times the distance. What if I can triple my speed? 9 times the distance, okay? That's why, I think I mentioned this to you earlier, a lot of sports equipment has become lighter at the expense of the M, but it's because you can swing the object faster and you get way more bang for your buck. So, okay. I mean, on a basic level, that's why, for example, golfers in the last 15 years, they're working out now and trying to build muscle because they realized it's club head speed. If you watch golf, they're hitting ridiculous distances now that 20 years ago people never would have considered. Some golf courses that are considered very traditional and pristine are becoming almost ridiculously easy because, they're clearing all the water hazards that we thought they had to work their way around, right? Hockey, very similar. What's your homework? Number 1? 2 is good, 3 is good. So 1, 2, 3. 4 is good. So far I've assigned them all. 5 is good. 6 is good. I'm probably going to, 7 I don't like. 8 you can skip. 9 you can skip. 10 is good. Skip 11. 12 is good. 13. Nah, skip 13. Here, I wanted to get to roller coasters or water slides. Water slides, another great example of conservation of energy. So 14 is good. So I ended up skipping 13, 11, 9, 8, 7. We're nearly done. I only have one more lesson. We're going to talk about the work energy theorem. That's the best way to calculate work. It's better than force times distance, but it's longer. So if you can use force times distance, great, but the work energy theorem is more flexible. You can use it in situations when you can't use force times distance.